Our next speaker is Evelyn Gaiser. She's the lead PI for the Florida Coastal Everglades LTER site, and they are in their 18th year of existence.
Well, thank you so much. It sure is a thrill to be here with the other speakers today to talk about issues of coastal resilience. When we think about coastal regions around the world, they're supporting half of our global population. They are producing services that all of us depend on. So we must be thinking about how to sustain these systems into the future. Hurricanes are common features of coastal ecosystems, and it's really difficult when you see a picture like that to think of them as resilience builders. We can all conjure up images in our minds of, the impacts that Hurricane Katrina had in New Orleans. Those are imprinted on our minds. Hurricane Andrew in Florida and Maria here in Puerto Rico. And even the smaller storms, the Category 2 Hurricane Wilma came through Florida back in 2005, and that really rearranged our lives. I'll just show you my backyard after that Category 2 storm. It blew down all of the exotic trees. My native trees were fine. And it also delivered a present to my front yard. I went out the front door in the morning, and gift from heaven. It was just the greatest thing in the world to find a trampoline, something I've always wanted, in my front yard. And so, all joking aside, it is difficult to think of these storms, even the small ones, as anything but devastating and rearrangers of our way of life. Indeed, how can big disturbances like this build resilience? How do we bounce back from this kind of devastation? Wendy, what are we being resilient to? What are the stressors that are occurring in coastal ecosystems that are so problematic? Well, when we think about resilience, most folks define that term in actually a lot of different ways, but a common one is the ability of ecosystems to sustain some form of identity despite perturbation. And the perturbation that's really affecting our coastal zone so much is sea level. One of the perturbations is sea level rise. And we're anticipating up to 1 meter more water by 2100. And Miami is going to be on the upper end of that prediction because for reasons that we're currently trying to understand, we've actually seen a quadrupling of the rate of rise in the last decade. Some 20 millimeters per year, not 3. And so that's causing our highest tides of the year to come up on the streets of Miami, and you've probably seen these images in the news. We also have saltwater creeping into the aquifer. We have a limestone base to the southern Florida, and that's very porous, and it allows for saltwater to very easily creep in to an aquifer that supplies 9 million people with fresh water. And that aquifer is recharged by the Everglades, which is also seeing increasing salinity over time, and our LTER record has been essential for capturing those changes. Even in the freshwater parts of our system, we are seeing increasing numbers of days where the marsh is getting salty. Now, freshwater plants and animals and the functions that they create are not able to handle saltwater exposure. It's an extraordinary osmotic stress. And as a result, we're seeing some really abrupt changes occurring in this ecosystem, including the appearance of these holes in the freshwater marsh. This is the sawgrass marsh. Sawgrass is the dominant plant in the central freshwater part of the Everglades. And when that plant sees salt, especially in the root zone and the pore water, the roots fall apart. And those roots are really important to stabilizing soils. And then the soils then are able to mobilize into the water column, where they then can decompose. And that causes us to lose elevation, making it even easier for the sea to intrude. And so this is an example of a positive feedback that we're just noticing in the last 10 years or so, and an example that's very similar to what we're finding in other LTER programs examining the effects of climate change. There's often these kinds of positive loops that happen. So how do hurricanes play into the story of rapid change in the system? Well, I want to talk about them primarily as resilience builders in the way that they help marshes actually maintain elevation gains rather than losses through physical and biological processes as well as human actions. And there are so many that are happening now as a part of Everglades restoration that are actually helping to build elevation in a system that right now is having some experiences that are causing it to collapse. And so when we look at the pattern of hurricane visits to Florida over the last about 100 years, we see that they're sort of a real magnet, this whole region, including the Caribbean, including the whole Atlantic seaboard that Meryl Albert is going to show you examples of. For these storms, and our LTER domain is just right in the heart of those trajectories. And it encompasses Everglades National Park. That's our Florida Coastal Everglades LTER site domain. And we see how we have sites arrayed along two major drainages called Shark Slough and Taylor Slough. The freshwater flows through freshwater marshes, including the sawgrass-based ridges, and then deeper water areas we call sloughs, and then into mangrove forests of varying stature, including some of the most productive forests on the planet. And then finally out into our estuaries and the Gulf of Mexico, traversing the incredible seagrass meadows of Florida Bay. And so just to set the stage, the template upon which these hurricanes reorganize our system, I just want to give you a few pointers about some unusual features of the system that are very important to understand to get the whole hurricane story. This is a little blow up of those two drainages, the Shark Slough and Taylor Slough, showing freshwater coming in from the top, moving through underground and over the freshwater marshes into the mangroves and out into the bay. And then saltwater marine pressures coming from this direction. And very importantly, the seawater doesn't just bring salt. It's also the main supply of phosphorus into this ecosystem that is incredibly limited in the amount of phosphorus that it has in the freshwater end of the ecosystem. The plants there are just completely starved of phosphorus, and so their productivity is very low. The productivity is shown in this orange line here. And as we get closer to the coast, we have this constant bathing of those coastal regions by the daily tidal action, bringing that phosphorus, essential plant nutrient, into the forests and fertilizing them. And so the productivity gradient is showing that. And for this reason, we call this estuary an upside down estuary. It functions really differently than most estuaries that bring nutrients from upland to the coast, okay? This estuary has been evolving and developing in this way for some 5,000 years. but it's been changing a lot in the last century due to the actions that we've taken in Florida. And I just wanted to show this image to show you how the historic flows had water moving all the way down from central Florida through Lake Okeechobee and into the Gulf very diffusely. And now we've taken all of that water, put it into thousands of miles of canals, and we dump it out into the ocean, and it's no longer going into the Everglades. Now, the federal government and state government realized this and the impacts it was having on the Everglades and the services that this system provides. A couple of decades ago, put together a plan to lift those impediments, remove those structures that are channelizing water that was to allow for all the development of agriculture and urban land uses to the interior, and reroute that water into the central Everglades. And it's a really exciting time for our program because we actually have some implementation of projects happening to refreshen the Everglades. And so this is the domain that our ecologists and scientists are studying. We do have folks from a number of different academic institutions working within our program and who have contributed to the slides that I'm showing you today. But we also work really closely with pretty much all of the agencies that I think are represented in this room, particularly on this interaction between climate change, biological functionality within the system, and water management, and especially the rehydration of the Everglades system by restoration. And so over the 18 years of our program, we've realized the importance of climate change and freshwater restoration actions on the ground and restructuring this ecosystem. But we've also picked up a huge signal of the impacts of a variety of disturbances, including hurricanes. And once again, this is the record of hurricanes that have come through our domain for the last some 100 years. And here's our period of intense study in the since 2000. And I'm going to tell you stories today about two major storms that have come through during that period. Hurricane Wilma in 2005, that we've had a nice 12 years to study the impacts of, and then just this last fall, Hurricane Irma that blew through. So here's Hurricane Wilma coming through, and it traversed the Gulf of Mexico and then blew right up into that Shark River drainage before it landed in Miami and delivered my trampoline. And it had significant winds. It brought a significant storm surge. And we were able to get out there a couple days later by helicopter, and we took a lot of pictures. And it was just extraordinary the way that the wind in the freshwater marsh, the wind had blown the stuff that I study called periphyton. This is an assemblage of microorganisms, algae, and bacteria that live in these big puffy mats that are like carpets over the vegetation and over the water surface. Well, the storm took all of that and blew it up against the ridges. So when we were flying over, you could really see the outlines of the ridges and the sloughs. And in studying that in the years subsequent to the storms, we're finding that the wind rows, we call them, are really important contributors to that ridge and slough topography that otherwise is degrading as a result of reduced freshwater flows. Well, the wind also really did a number on our coastal forests, defoliating those trees, and we've been able to measure the opening of our forests as a result of all the down trees and the defoliation, and we use LiDAR to do that. In this image, all the little blue holes are openings in the canopy that if you look up into the sky, normally this would be very shady, and you can see this major opening that allowed for the little seedlings. We had a lot of propagules, the little mangrove seeds, distributing into the system with the surge from the storm. and then they were able to settle there, have lots of light, and grow very well, and even migrate further to the interior where they can then build soil and build elevation. Well, we've been doing a lot of modeling to understand the extent to which storms of different magnitudes affect, surges of different magnitudes affect storms of different types. And we're finding that these red mangrove forests, shown here, are just really great at attenuating the energy of storms. And they also are super great at trapping any kind of muds and sediments that get delivered with surge. And we were able to go out there and take some sediment cores and sample those muds, and we found that throughout the mangrove zone, we found some 3 to 5 centimeters of mud on top of the mangrove peats. And that mud was full of the phosphorus from the Gulf of Mexico, sort of the upside down estuary showing itself. And this is just an image of the rate of soil accretion in these forests, showing that before the storm, we were barely keeping up with the pace of sea level rise. And then the storm comes in, dumps 4 or 5 centimeters of mud, and that mud accounted for was equivalent to about 50 years of the mangrove forest-based soil accumulation. And that mud stayed there, but the stuff in it, the phosphorus, leached out into the water and moved very easily with the tides all the way up into our freshwater regions for like 10 years. It left a huge legacy of natural fertilizer from this upside down movement of nutrients. That then, of course, was a wonderful stimulant for those little trees to really recover after the storm. And we were able to document that in a lot of different ways, but including with the eddy covariance tower that is a huge tower, 100 feet tall, arching over our mangrove forest with a little sensor on it that measures the amount of carbon dioxide that is breathed in by the forest. Our tower fell down with the storm and we had to create a new one afterward. But what we found was that within about 5 years after the storm, the forest had fully recovered its functionality. And that was because these little trees had access to all that phosphorus-rich mud below them and an open canopy with lots of light coming in. And they grew really, really fast. And the forest is now back to functioning as it was. So we had about 12 years of relative solitude to study those impacts before another big storm came our way. And this is Hurricane Irma that barreled in. It was a Category 5, one of the biggest and nastiest storms to ever be seen, and yet it quieted down a little bit before it came in a very similar trajectory to Hurricane Wilma. And yet when we saw it on the radar, pretty much everybody was like, we have to get out of Dodge. And yet before we left and before the national park closed, we ran out and we tried to recover as many of the fancy instruments and expensive stuff as we could, except for the instruments that had snakes wrapped around them. That's a true story. And then we found that we were not the only ones. Pretty much everybody left, but we weren't the only ones to leave. We have a couple hundred fish that are going around with these acoustic sensors in them. And we're now using acoustic telemetry to track where they are. We have a whole bunch of these receivers in the water, and every time a fish swims by, we know exactly where it is. So we had a bunch of shark with these tags, and we were able to see these sharks move up to 100 kilometers away. How do we know that? Well, a lot of folks are using these acoustic arrays now, and they showed up in an array of one of our partners of the Gulf Coast. And then they came back. They came back within a couple of weeks of the storm. our snook, which is a really important recreational fish that had taken a lot of hits. We had a cold snap years ago in 2010, killed a lot of them. And then we had a number of years of drought combined with not enough fresh water moving through the Everglades. They were doing terribly. And then the storm comes in and it reconnects up all of the little marshes to the interior that these fish love to go in and feed in. And we had the biggest recruitment that we've ever seen in the history of record of all of these little fish that had moved into the estuary, and that snook population is now recovering in a massive and very exciting way. We found that not all organisms sense the storm's arrival. Just like people, we always have the guys down in the Keys who, I think the technical term is hunker down, right? People hunker down through the storm, and we found that that was true of some of our animals as well, especially the gators. We have a lot of them tagged, and they just didn't care at all, and they stayed within like a kilometer of their home range. So, they don't care. In addition to like advancements in acoustic telemetry that we've been able to use in the past 10 or so years, we've also had a lot of advancements in instrumentation to detect landscape scale changes. We can now fly with LiDAR equipment and get really great imagery of our forests. And NASA has been supporting this work. David Lagomasino is here in the crowd who conducted a lot of these flight lines. This is superimposed on top of our storm surge model of Hurricane Irma and the path of the storm there. So they had done a number of transects in the past few years to document forest structure, including some of these collapsing features that are going on. And it was really neat to be able to get back out there after the storm and compare that imagery and be able to quantify at the landscape scale the magnitude of canopy loss. And this is looking down onto the forest with those cameras. And this is just spectacular imagery. I would love to show a lot more of it. The storm didn't just have wind effects in the system, it also delivered a significant surge. But interestingly, the water retreated before it came in with a vengeance. And just like the gators, we had a few researchers hunkering down in the Keys who went out and took this picture, the upper picture of Florida Bay, right before the storm, when all the water had been drawn out of Florida Bay. Then came back in and caused all of our seagrass to mobilize into the water column, and you can see it floating on the surface there. The storm, just like Wilma, brought that major surge in, and it brought a lot of mud from the Gulf of Mexico. So with help from NSF, a nice rapid grant, we've been able to get out there along a number of different transects and really quantify the extent of that surge deposit, because we've learned how important it can be. It's full of phosphorus that is going to help that forest recover. Well, the storm also had significant rain associated with it. We had some 20 centimeters of rain in the upper watershed in a single day. And that water moved down into the upper reaches of the Everglades. This is one of our tall technicians up to his neck in water, hardly able to get up onto the platform there. And this was super interesting because that water was able to move into the Everglades because of two bridges that have been constructed within the last few years, a part of Everglades restoration. And those bridges had not been operationalized, but they needed, the Army Corps issued an emergency operation plan to get the water off the landscape. Those floodwaters ran through the bridge and into the heart of the Everglades, bringing with it a lot of mud, a lot of carbon in the water that we are quite concerned is being generated by these gaps that are forming in the heart of the interior of the Everglades. So there's an interesting interaction potentially going on there. Hurricane Wilma did not have this kind of export associated with it. But since we've seen these losses going on, we're worried that that's carbon that's exporting from the interior of the Everglades. So just to wrap up, the coastal resilience story in the Everglades is one that couples the actions of people, in reaction to sea level rise that's moving salt to the interior, reducing elevation in some of these areas that are very sensitive to salt. Freshwater restoration rehydrates these areas with fresh water that we're doing many different kinds of experiments to understand the effects of and the ability of freshwater rehydration to reverse or at least slow down these losses. And then hurricanes come in. They deliver mud, they deliver nutrients, they deliver propagules and recruits, and enable the system to recover in ways that we had never anticipated. And so I want to end with a question of whether hurricanes deliver trampolines to the Everglades that allow the system to bounce back from all of the assaults that the Everglades has experienced. How better to study this than through long-term ecological research? Thanks so much.
We do have a couple minutes for questions, so if you bounce out of your seat, you can come up to the mic. I do want to remind you, please tell us who you are and where you're from before you ask the question. So, open it up.
Good morning, that was a great talk. I'm Rick Schwartfeger, I'm a program director here at NSF in the SBIR program. Also Florida resident, still living in a rental, waiting to get my house rebuilt after Hurricane Irma.
Okay.
So my question is, not really directly related to hurricanes maybe, but I'm wondering what the impact of hurricanes is on the horrible red tide problems we see in Southwest Florida.
Right on. Well, so there's a lot of water moving out of Lake Okeechobee as well. Lake Okeechobee has accumulated hundreds of years of phosphorus in it from all the agricultural activities around it, and that water exits out the canal structures into our estuaries along the coastlines. And we have seen the signs of similar kinds of blooms that have occurred in the past, nothing like the 2015 drought gave us, but it's certainly a worry, and we have researchers studying the toxic algae that are blooming there. So yeah, it's a real concern. Excitingly, we do have the legislature, federal legislature just approved the creation of a great big reservoir south of Lake Okeechobee to hold fresh water. That's really going to alleviate that coastal efflux of nutrients. And so we're excited to see that be approved and hopefully move into action fairly soon.